For as long as we've had video games, they've been boxed in by the limits of silicon. But what happens when you throw out those rules and bring in the weird, wild world of quantum mechanics? Well, today we're going to look at how quantum computing is getting ready to totally transform interactive entertainment. So here's our game plan. We'll start by looking at the walls today's games are hitting. Then we'll check out the new toolkit making all this possible, CUDA-Q. After that, we'll dive into how it could completely change in-game physics, lighting, and AI. And finally, we'll look at the roadmap to get us to truly quantum-native games.
All right, let's get into it. You know, modern games look absolutely incredible, but even the most advanced titles are starting to bump their heads against a really fundamental technological ceiling. I mean, think about it. Have you ever been playing a game, and even with the jaw-dropping graphics, something just feels a little bit off? You know, maybe it's how two objects crash into each other, or the way light just doesn't look quite real, or how the enemies always seem to do the same thing. We are so close to realism, but we're just not all the way there yet. And this slide, right here, gets to the very heart of it. On one side, you have our current classical limits. That means physics based on clever approximations, lighting that's often just a fancy trick, and AI that's really just following a script. But on the other side, you've got the quantum potential. We're talking true simulation, photorealism that's indistinguishable from reality, and AI that feels genuinely alive. That's the quantum leap we're talking about. So how do we actually make that leap? Well, it's not magic. It's about having the right tools for the job. And for game developers, that new tool is NVIDIA's CUDA-Q. You can think of CUDA-Q as the essential bridge to this new world. It's an open-source platform that lets developers write code for a hybrid system, one where your trusty old CPUs and GPUs can work right alongside new quantum processing units, or QPUs. The really key thing here is that it brings all three of these processors together under one roof, with a single programming model. And here's how it fits into a game engine you'd recognize today. The CPU is still the main brain, handling the game's logic. The GPU is still the workhorse, crunching all the graphics. But now, we can hand off certain super tough problems to a brand new coprocessor, the QPU. And that QPU runs special little programs called quantum kernels. So what is a quantum kernel? Well, this is the really clever part. If you're a developer watching this, just think of it exactly like a CUDA kernel that you'd send to a GPU. It's a specific piece of your code, a function you can call up, that gets sent over to the quantum hardware to do its thing. It's a familiar workflow for a completely new kind of computing. Okay, let's look at our first huge application, physics. We're talking about taking the physics in games and making them behave exactly like they do in the real world. See, deep down, every physics engine is constantly solving a gigantic math problem. Every single frame. To make a stack of barrels tumble just right, or to make a car crash look convincing, the engine has to solve a huge system of linear equations. You might see it written as AX equals B. Now, the classical way to do this is with methods like projected Gauss-Seidel, or PGS. It basically works by making a series of educated guesses until it finds an answer that's good enough. The quantum approach, though, using an algorithm called HHL, can find the perfect solution directly. And this isn't just a bit faster, it's an exponential speedup. It's a totally different universe of performance. Okay, but here's the catch. The HHL algorithm, in practice, has some pretty big hurdles. Just loading the data into the quantum computer is really expensive, and the answer it gives you comes out as a very delicate quantum state. It's a bit tricky. That's why, for right now, researchers are focusing on near-term solutions, like variational quantum linear solvers, or VQLS, which are a much better fit for the kind of quantum hardware we have today. Next up, lighting. This is easily one of the biggest performance hogs in any modern game, and it's an area where quantum computing could make an absolutely massive difference. 33 million. Just let that number sink in for a second. That is roughly how many lighting calculations, or samples, a game has to run for a single frame of 1080p gameplay, just for a common effect like screen space ambient occlusion. It's a total brute force method, and it just eats your GPU for lunch. The quantum solution, on the other hand, is way more elegant. It's an algorithm called quantum amplitude estimation, or QAE. Instead of just throwing more and more samples at the problem, it uses the weirdness of quantum mechanics to get to the same answer with way fewer calculations. And this is where the real magic is. See, a classical Monte Carlo method needs to square its number of samples to get more accurate. The quantum version only needs to grow linearly. So what does that mean in the real world? It means that to get the same image quality that takes 16 samples with the old method, a quantum computer could do it with just 4. That is a huge savings for the exact same result. All right, on to our last big example, AI. Let's talk about how we can breathe actual life into game characters and create AI that's genuinely smart and unpredictable. A lot of game AI these days runs on neural networks. But to make them really sophisticated, you have to train these massive models with thousands, sometimes millions of different parameters. And that training process is incredibly slow, it's expensive, and at the end of the day, you often still get an AI that feels, well, robotic. Just look at this comparison. It's incredible. A pretty standard neural network might need around 8,000 parameters to do its job. A variational quantum circuit, or VQC, can achieve an amazing amount of complexity with just 80 parameters. 80! So how is that possible? Well, a classical network can approximate any function, which is cool. But a quantum circuit operates in what's called an exponential Hilbert space. Basically, every single qubit you add gives the circuit a whole new dimension of possibilities. It can represent way more complex information with way fewer moving parts. And fewer parameters means faster training, and the potential for AI that can truly surprise you. So, we've seen all this mind-blowing potential. But how do we actually get from the experiments we're running today to a future where games are built from the ground up to be quantum native? And this is the really crucial reality check. Right now, all of these amazing speedups we're talking about are being done by using super powerful GPUs to simulate a quantum computer. We aren't quite at the point where we can run a real-time game on a big physical QPU. Not yet. But the path forward is actually really clear. Today, we're in what's called the NISQ era. That stands for Noisy Intermediate Scale Quantum, and it's all about that GPU simulation. In the near future, we'll start seeing those hybrid systems, where real QPUs work alongside our CPUs and GPUs. And the long-term dream, the end goal, is the era of large, fault-tolerant quantum computers that can chew through these problems with ease. This quote from the research paper really says it all. The work being done today isn't about finding some magic quantum switch to flip on. It's about doing the hard, foundational research right now to figure out which parts of a game engine, whether it's physics or lighting or AI, are the absolute best places to use a quantum computer once the hardware is ready. And that all leads us to the most exciting question, doesn't it? When physics are no longer just a good enough approximation, when light behaves exactly like it does in our world, and when an AI opponent can think and adapt in ways that feel truly alive, what new kind of game does that even make possible? This isn't just about making the games we have today look a little better. It's about opening the door to entirely new ways to play that we can't even begin to imagine.